Hello friends, in previous lectures you saw about stability augmentation system, how the roots were to be changed, how roots are changed using stability augmentation system, and what will be the benefits of using stability augmentation system. We will be seeing some numericals based on this stability augmentation system to make the concept more clear to you. So for that, let's take a aircraft which is constant to yawing motion. Let's see what will your stability augmentation have effect on that motion. So as you already seen in previous lectures that the equation, differential equation for yawing motion was given by delta psi double dot. Don't get confused with this delta, this represents your perturbed variables. You can write delta psi dot or psi dot in small, it will be same. I prefer using notation delta of psi dot. Delta of psi dot equals to your differential equation with respect to yawing motion was delta psi dot equals to n beta into delta of beta plus n beta dot into beta dot plus n r into delta r plus n delta r into delta of delta r. As you know, you can write, since the body is constant for yawing motion, so you can write delta psi equals to delta beta, delta psi dot equals to delta of beta dot, and delta psi dot equals to delta of r. So this is minus beta, delta psi equals to minus of beta and minus of beta dot. Further using this values in my differential equation, your differential equation will become delta psi double dot minus nr minus n beta dot into delta of psi dot plus n beta into delta of psi equals to delta n delta r into delta of delta r. So this is your differential equation. By seeing this, you can tell this is a second order differential equation. The value of zeta for this differential equation will be minus nr minus n beta dot divided by 2 omega n, where omega n will be root over n beta. So this represents my damping ratio and natural frequency. Now suppose I want to change the value of natural frequency. So as per your stability augmentation system, I will be writing your state variables in terms of my input parameters. So let me write delta rs minus k of delta psi, k1 of delta psi. Substituting this value in my differential equation 1, you will be getting delta psi of double dot minus nr minus n beta dot delta of psi dot plus n beta delta of psi equals to value of delta r equals to minus n delta r k1 delta psi. Further, this can be written as delta of psi dot double dot minus nr minus n beta dot into delta of psi dot plus n beta plus n delta r k1 into delta of psi equals to 0. Now from this differential equation you can see the value of omega n is root over n beta plus n delta r into k1. Using the required value of natural frequency, you can easily determine substituting the required value of omega n here, and as you know these are already given for original equations, so you can determine the value of k1. And similarly your zeta will be minus nr minus of n beta dot by 2 this new value of omega n star. So you can see by substituting your value of delta r in terms of state variable you want to change, you can change your system, new systems zeta and omega n. But see that still your real part is same, since you know that for any second order system your roots will be given as, for second order system represented by 2 zeta omega n s plus omega n square. Roots are given as minus 2 zeta omega n plus minus I omega n root over 1 minus zeta square upon 2. So since zeta and omega n term is same in this equation in which we use stability augmentation system, and zeta omega n is same even in the original differential equation, so real part will be same, so you can say the decaying rate will be same, only the frequency, the natural frequency will change in these both equations. Suppose I want to change both your value of damping ratio as well as natural frequency, we will be using two values of k1. One will be with respect to zeta, another will be with respect to zeta dot. I will be showing you in this coming calculations. Suppose I wanted to change omega n and zeta at the same time, so I will be taking two values. I will be taking your input signal, that is rudder deflection, with respect to your state variables delta psi and delta psi dot, because this will be with effect to your natural frequency and this part will be for changing your zeta. So the new value of your rudder deflection in terms of state variables will be delta r equals to minus of k1 delta psi minus of k2 delta of psi dot. Now substituting this value in your differential equation 1, the new differential equation which you will get is delta psi double dot minus nr minus n beta dot delta of psi dot plus n beta delta of psi equals to minus n delta r k1 delta psi minus n delta r k2 delta of psi dot. Further solving this, delta psi dot minus n r minus n beta dot minus n delta r k2 delta of psi dot plus n beta plus n delta r k1 delta of psi equals to 0. Now from this equation you can see the new value of omega n2 star is root over n beta plus n delta r k1, and new value of zeta 2 star, this is star, equals to minus of nr minus n beta dot minus n delta r into delta r of k2 divided by 2 omega n2 star. Now, using this value of k1 and k2, we derived at the new values of zeta and omega n, and similarly as derived for this particular set of variables, if you want some desired value of zeta and omega n, just put this values required value of zeta omega n here and zeta 2 here. These are two equations are there. You can solve the you can get the value of k1 and k2. Substitute that in this equation, and you will get your response as per your new zeta and omega. We will be taking an example based on this, so the concept will be more clear to you. So let's take an example of changing the value of zeta omega n as per the requirement of the pilot. For aircraft which is constrained to yaw motion, as you have already derived, the differential equation will be aircraft constrained to yaw motion. The differential equation was given by delta psi double dot minus of nr minus n beta dot into delta of psi dot plus n beta into delta psi equals to n delta r of delta r. The values for n beta equals to 1.77 per second square, and r equals to minus 0.10 per second, and delta r equals to minus 0.84 per second, and beta dot equals to 0. This is a numerical from Nelson Flight Stability and Automatic Control System, chapter 6. You can go and check there. Now, using these values and substituting in the differential equation, I will get psi double dot minus of minus 0.10 minus 0 of delta psi dot, and beta is 1.77 delta of psi equals to, and delta is minus 0.84 of delta r, which gives me delta psi double dot plus 0.10 delta of psi dot plus 1.77 delta psi equals to minus 0.84 delta r. Now, the value of omega n from this equation will be omega n will be root under 1.77, which is equals to 1.33 radian per second, and zeta will be 0.10 divided by 2 into 1.33, which will give me 0.037. Now, you can see the value of zeta is very small. So, the nature of my graph will be, since it is a second order system, so if I give it a step response, it will be some oscillations about this, your step input, say about 5 degree, it will be response will be of this nature, and since your damping ratio is very small, so the oscillation will sustain for a very long time, and it will take a very large time to settle down. So, this is not a desirable property in terms of controlling an aircraft or stability of an aircraft. The pilot wants the oscillations to die rapidly. So what we'll be doing, we'll be using stability augmentation system to change the value of zeta to some desired value, so that the oscillations die quickly and the response is better. So let's design a stability augmentation system. Since we want to only change zeta, so we will be using only one variable, and to change that, you have already seen what are the flight handling qualities of an aircraft. So pure yawing motion, say let's take zeta equals to 0.2. So for designing stability augmentation system, I will be writing your delta r in terms of state variable. So my value of delta r will be minus k of delta psi dot. On substituting the value of delta r in my initial equation, equation 7, in equation 1, the new value of zeta omega n will be, or the differential equation will become delta psi double dot minus nr minus m beta dot minus k n delta r into delta psi dot plus n beta delta psi equals to 0. Since substituting the values of nr, n beta dot and delta r, my differential equation will be psi dot minus nr is minus 0.10 minus 0 minus k, c n delta is minus plus 0.84 into delta psi dot plus n beta is 1.77 delta psi equals to 0. Again, the value of omega n will be root over 1.77, which is 1.33 radian per second. Now value of zeta will be minus 0.10 plus k into 0.84 divided by 2 into 1.33. Since the desired value of zeta is 0.2, this value, this is the desired value. So I will substitute that value in the desired value of zeta, it is, which is 0.2 equals to minus 0.10 plus k into 0.84 by 2 into 1.33, which will give me the value of k as minus 0.154. So using this value of k, you can change the value of zeta to your desired value. In this case, it was 0.2. Now we saw an example based on stability augmentation system, and previous lectures you have seen about transfer functions, how to derive transfer function with respect to state variables. So let's see a system, short period dynamics, in which the damping ratio is very less. We have to change the damping ratio so the system resolves as per your desired requirement. So your change of angle with respect to elevator deflection is given by transfer function alpha upon delta E. This represents my system dynamics. Your input is delta E, which is given by pilot, and your output is angle of attack. Now this is an open loop system which gives your directly angle of attack when an elevator input given to this system. We have seen this. This is a transfer function. So you can directly plot the response as we have seen using a step response or impulse response. Now I want to change the dynamics of this system. This can be changed using some control systems, or you can say a closed loop system. Now the SAS is nothing but a closed loop system, which is represented as, this is my transfer function alpha upon delta E. This was my input delta E by pilot. This is my summer. My output is angle of attack. I will be tapping this. I will be multiplying this with some constant k, and this is your feedback. The net out input which this transfer function or system will be receiving is, this is due to delta E SAS. This is delta E pilot minus delta E due to SAS. This is your closed loop system, which changes the location of your eigenvalues or roots. So your natural frequency and damping ratio changes according to the value of k you provide, which is the desired value of omega n and zeta. So let's take a numerical based on this system. Suppose for an aircraft the short period mode is very poor. I have to design a feedback system so that my desired roots is minus 2.1 plus minus 2.14 I. These are the desired roots which is required by my system. Your system is given by delta alpha dot by delta q dot, this is for short period, equals to minus 0.334, 1.0 minus 2.52 minus 0.387 into delta alpha into delta q plus minus 0.027 minus 2.6 to delta of delta E. As we have earlier seen, this is in representation of state matrix, which is given by delta x equals to A delta of x plus B delta of u. This is your known as system matrix, this is known as control matrix. So for this particular state representation, what will be the eigenvalues of this state space matrix? You can easily determine using lambda I minus A. This is your A matrix. Determinant of this equals to 0, which will give me, for this A matrix, lambda plus 0.334 minus 1, 2.52 S lambda plus 0.387. Determinant of this equal to 0. We will get characteristic equation as lambda square plus 0.721 lambda plus 2.6492 equals to 0. The roots of this characteristic equation equals to minus 0.3605 plus minus 1.587 I. From this characteristic root, you can find the value of omega n, which is root over 2.649, which will give me 1.627 radian per second. second, and zeta will be 0.721 divided by 2 into 1.627 equals to 0.039. You can see from this the value of zeta is very small. Now I have to change this value so that the roots of my new characteristic equation is given by this. So I will be writing my value of delta E in terms of state variables alpha and q. As derived earlier, for stability augmentation, the new matrix which is given as, it is x double dot equals to A minus B K transpose, or K as already told, into delta of x. So in this question, your B matrix is given by minus 0.027 and minus 2.6. Your value of K transpose or K, it's K1 and K2. Now substituting these values, the new system matrix will be A minus B K transpose equals to your minus 0.334 plus 0.027 plus into K1, 1 plus 0.027 K2 minus 2.52 plus 2.6 K1 and minus 0.387 plus 2.6 K2. The characteristic equation for this new system matrix will be lambda I minus the value of this characteristic matrix or the new matrix. So now new characteristic equation is lambda I minus A minus B K transpose, determinant of this equals to 0, which will give me lambda plus 0.334 minus 0.027 K1 minus 1 minus 0.027 K2, 2.52 minus 2.6 K1, lambda plus 0.387 minus 2.6 K2, determinant of this equals to 0. Further solving this determinant, you will get lambda square plus 0.721 minus 0.027 K1 minus 2.6 K2 into lambda plus 2.65 minus 2.6 K1 minus 0.8 K2 equals to 0. This is the characteristic equation of my new matrix, and since the roots of this characteristic equation should be as per desired, the value minus 2.1 plus minus 2.14i. So the characteristic equation using this as your root will be desired characteristic equation for desired lambda is given by lambda square plus 4.2 lambda plus 9 equals to 0. This is a characteristic equation using the roots as minus 2.1 plus minus 2.14i. Now comparing the coefficients, 4.2 equals to this coefficient and 9 equal to this coefficient. 0.21 minus 0.027 K1 minus 2.6 K2 equals to 4.2, and 2.65 minus 2.6 K1 minus 0.8 K2 equals to 9. Solving these equations, you will get the value of K1 as minus 2.03 and K2 as minus 1.318. So your delta E in terms of K1 and K2 and state variables alpha and Q will be written as delta E equals to 2.03 delta alpha plus 1.318 delta Q. So you can see, using your delta E and the value of K1 and K2 with state variables, you can change the roots of particular equation, the value of zeta and omega n as per your desired system. So SAS is a very useful technique to change the value of your natural frequency and zeta, just using a small gain in terms of your state variables. So using this system, you can change the response of an aircraft according to your convenience or according to your needs. I would like you to practice more problems on stability augmentation system. Thank you.